here we go, kinetics. Those of you who are here, it's good that you're here because this is totally new, brand new. And it's not, really, this stuff is not all that difficult, I don't think. It's fairly intuitive because we're just talking about how fast reactions occur. But it's going to be different than anything that you have experienced in chemistry so far because we just have not talked about this at all, okay? It makes you feel any better, a lot of times they cover this in first-year chemistry classes because it's really not that hard. So we're easing you into it. Once we get into the equilibrium stuff, it gets a little bit tougher. But this stuff we talked about today, so we don't need to really belabor that. But if you are wanting to, write this down on your, well, it's in the book, so I wouldn't worry about writing it down right now. But the physical state, the concentration, the temperature, and the presence of a catalyst are the four main things that we're going to talk about that would influence the rate of a chemical reaction. And when I say physical state, there's a few things that are kind of included in that. That's obviously the actual state of matter that it's in, okay? A lot of reactions happen better when things are gases than they do when they're solids for fairly obvious reasons, right? When you have gas molecules, there's a lot of different possibilities of ways that they collide with one another. When you have two solids together, they can only react on the surface because those are the only molecules that are coming into contact. So gases and liquids are going to tend to do better as far as reacting faster. But then also included in physical state are things like the way that the molecules are turned when they hit one another. And we'll talk about this more when we get to collision theory, but if molecules aren't turned in the correct orientation, they won't react. So they have to be turned correctly in order to be able to react when they hit. Other things included in physical state, surface area. How much surface area do you have? I guess I sort of already covered that when we were talking about gases, liquids, and solids. But all of those ideas are included in the physical state part. And then concentration, temperature, and catalyst are pretty straightforward. So there's that, and then this just goes into a little more detail. But since we talked about that today in class, I think we can hurry on here because we've got plenty to do with the rest of this stuff. So when we want to measure the speed of a reaction, we're measuring the change in concentration versus time. Okay, for a reaction. Now, the rate that you've been most familiar with up to this point is what? Let me think of a rate that we use on a daily basis. Miles per hour, right? So our speed, okay? So speed is distance over time, okay? Well, it doesn't make a lot of sense to talk about distance in chemistry when we're talking about a reaction happening. So instead of talking about distance over time, we talk about the change in the concentration over time, okay? You can look at this from a couple different perspectives. You can think about it as the change in B over time, or you could think about it as the change in A over time, right? Either one of those is going to help you measure the rate of this reaction. So you can kind of choose. I will say typically, I don't know why, it's weird that they show the change in the moles of B over time here, because typically we look at it with respect to the reactants. How fast are the reactants disappearing from the reaction, okay? But you can look at it either way. It doesn't really matter. Is this making sense so far? It's fairly straightforward. We just need to measure how much is the concentration increasing or decreasing over time. Now, by the way, which one of these is the concentration going to be decreasing over time? A, right? Because A is reacting to form B. Okay, so then the concentration of B is going to be increasing over time. So you would expect to have a negative rate if you're looking at it with respect to A, and a positive rate if you're looking at it with respect to B. Does that make sense? Okay, because the rate is, or the concentration is decreasing for A, it's increasing for B. Okay, so here's an example of a reaction happening. You've got all A to begin with, and then as A starts to, I guess maybe it's decomposing here. I'm not sure exactly what's happening, but some B is now forming, okay? And so then eventually over time you end up with, actually it looks like in that last one you end up with more B than A. And if you let the reaction go to completion, then eventually you would have all B, okay? So at time 0, let's say there's 1 mole of A, which is 100 red spheres, and there's no B at all. Okay, at time 20, then we've got 0.54 moles of A and 0.46 moles of B. At time 40, and these are minutes, then there's 0.30 moles of A and 0.70 moles of B. Now again, your time can be in minutes, it can be in seconds, it could be in hours. It just depends on, you know, how you're going to measure the rate, how fast the reaction is occurring. Typically, we're going to measure in seconds, but we can measure in minutes too. So then if you want to find the average rate, okay, the average rate is going to be the change in the moles of B over the change in time, okay? So if we want to find the rate at, and that's overall, okay? So if we want to find the overall average, and this really is very analogous to speed, okay, if you've taken a physics class, you end up with 0.70 moles of B, so you'd take 0.70 minus 0, because there's none to begin with, divided by the change in time, okay? And are you distracting other people? All right. So that would give you your average rate. Now, if you want an instantaneous rate, or if you want an average rate maybe just from 0 to 20 or something like that, it just depends on what time you're looking at. Then you can, you know, you can figure out different rates here. Okay. So the rate that they're showing here is an average rate from 0 to 20. Okay. We could find a different average rate from 20 to 40. We could find a different average rate from 0 to 40. Okay. So it just kind of depends on what part of the reaction you're looking at. By the way, we'll come back to this later, but what would you expect maybe to happen to this reaction over time as far as the rate of the reaction? Seems like it would probably slow down, right? Now, what's the reason that a reaction tends to slow down over time? Yeah, the reason it reacts is because the two things are coming into contact with one another. Now, with this reaction, looks like maybe a decomposition, so this may be a little different than normal. But typically, when you've got two things colliding to form a product, the more they react and form the product, the less of the reactants there are to hit one another, so that's going to slow the reaction down. Okay? So typically, over time, these reaction rates will slow down. And we're going to talk about that more later. For A to B, again, you can measure, and I just mentioned this, so I won't belabor the point, but it's going to be a negative rate if you're talking about it with respect to A. It's going to be a positive rate if you're talking about it with respect to B. This, again, is normally the way that we measure rates. I don't know why they introduced it with B in this set of notes, but they did. But there's your average rate, okay? So it's just change in moles of either the reactant or the product. So example problem here for the previous reaction, calculate the average rate of disappearance of A over the time interval from 20 to 40 minutes. Okay. Now again, this isn't hard. From 20 to 40 minutes, we're calculating the disappearance of A, right? So we would take the 0.5, or actually the 0.30 minus 0.54, right? Because you need a negative number there. And then you divide that by the time, which is 20 seconds. That would give you your rate. Okay. I'm pretty sure that is a sample problem in the book, so I won't go over that one because, again, I want to make sure we get through everything here. This part we already talked about, this first bullet, so it's, I don't know, it got cut off here. Most useful units are probably molarity, not just number of moles. You can use number of moles, but molarity tends to be better. And since in most of these situations the volume is constant, then molarity and moles are going to be directly proportional to one another, okay? Since the volume is not really changing in most of the scenarios that we would have in our stuff that we do in class. So here's a reaction. This is an actual reaction rather than just an A to B thing. And here's some data for that reaction, okay? So if we're looking at that, at time 0, we've got a concentration of 0.1 molar of the C4H9Cl, okay? Now notice, as time goes on, that concentration goes down and down and down and down, but look what happens to the rate of the reaction. You notice what happens here? It also decreases, right? Just like we predicted that it would, as the reaction continues, then the rate of the reaction tends to decrease over time, okay? Okay, now we can calculate the average rate in terms of the disappearance of the C4H9Cl, which again, that's normally the way that we do it, is we calculate how fast is the reactant disappearing. And usually you just pick one of the reactants and you measure it with respect to that. it's much easier to do it that way than to try to pay attention to both reactants at the same time, or reactants and products. So the units for average rate are going to be molarity over seconds, or if you prefer, moles per liter times second. And the way that that would be written, moles per liter times second. Liters and seconds are on the bottom of that equation. So I don't know why, but on the AP exam in the past, they've made a big deal about units in this particular section of the class. So for kinetics, units are a big deal. You always want to make sure that you're putting your units. You're going to get questions sometimes about what are the units for the rate constant, what are the units for this rate, those sorts of things. They want it for whatever reason, they want to make sure that you can deal with units in this section. I think they just want to make sure you can deal with the units in general, and this section tends to be a little confusing with the units, so if you can do it here, they figure you can do it anywhere. I think that's kind of the rationale. So just pay attention to your units is what I'm saying. Average rate decreases with time. We notice that. You can plot the C4H9Cl versus time. The rate at any instant is the slope of the tangent to the curve, so you can find an instantaneous rate if you find slope. And so they're just kind of explaining to you how, because for the rest of the problems that we do, they're typically going to give you the instantaneous rate, so they're just explaining to you how they find that, okay? They're just graphing this thing versus time, and you get a graph like this, okay? And so then what you can do is draw a tangent to the curve at any point, and the slope of that line, that's the tangent line, that's going to give you your initial rate. yeah. So this is fun math stuff here. So that's how you get your instantaneous rates, okay? Anything else I want to say there? Instantaneous is different from average rate, obviously, okay? But when we talk about rate from here on out, we're typically talking about the instantaneous rate. So just be aware of that, okay? We're not really talking about average rate anymore, even though that's, again, how we introduced it. We're talking about instantaneous rate, okay? All right, so reaction rate and stoichiometry. Just a little bit here. You need to be aware of this, okay? And they made a fairly big deal about this on the old AP exam. I don't know how much of this you're going to see on the new one, but I feel like I need to teach it just to be safe. Using the previous graph, calculate the instantaneous rate of disappearance at time equals 0. Oh, why is that listed as stoichiometry? Okay, never mind. We're going on. Here we go. Okay. So for the reaction, this is nice because the stoichiometry here is all 1-to-1, right? So they're saying the rate of disappearance of the C4H9Cl is essentially equal to the rate of the appearance of the C4H9OH. Now that wouldn't necessarily be the case if this is not 1-to-1 stoichiometry, right? Which, I mean, that should make sense, right? If this was, say, a 2 here, okay, now it's not. This is unbalanced. I just made it unbalanced, but don't worry about that. Let's say that was a 2. Then this would be appearing 2 times as fast as this is disappearing, right? Okay? So you just have to keep the stoichiometry in mind if you're relating the appearance of one thing to the disappearance of another. Now, I hope this doesn't confuse you because later on I'm going to tell you that we can't get the rate law from the stoichiometry, okay? But if you already know the rate of one thing, you can compare it to the rate of the others using the stoichiometry. Yes, sir?
Just like there is, this is sort of on topic, sort of not. It's
Okay.
Just like there is a catalyst. What do you call like something the opposite of a catalyst, or like?
Oh, okay. So the question was, what do you call the opposite of a catalyst? It would be called an inhibitor. We don't really deal with those in here. We're usually just talking about catalysts in this class, but that's typically what it's called. Preservatives are examples of inhibitors. Yeah, they load their fries at McDonald's with inhibitors, so you can find them, months later underneath your car seat, and they look the same as they did before. So, yes.
Is that only when the volume is?
Okay, so can you compare the rates like that when the volume stays the same? Yes, if you're doing it with in terms of concentration, then that is correct. Yeah. So if the volume changes, that would change the molarity, and that would make a difference. Okay. So you're assuming here that this is happening in a, in some sort of container that stays at a constant volume. Yeah. Now, if we wanted to take out the volume issue, then we could just measure the change in moles instead, right? And then we wouldn't have a volume concern. The only reason that's a concern is because it's molarity instead of just moles. So if our stoichiometry is not 1-to-1, don't let this confuse you too much. I think it's better usually to just think about what I just told you, the 2-to-1 idea, okay? But, I mean, technically this formula does work. If you take 1 over the coefficient in front of A times the concentration, that should be equal to 1 over the coefficient of B times B's concentration, equal to C equal to D. Now notice there's a negative sign in front of A and B, but not in front of C and D. Does that make sense? Because as the reaction occurs, A and B are disappearing, right? C and D are appearing. Okay? Whew, we do not have enough time for this. So the rate of disappearance of ozone, how is it related to the rate of appearance of oxygen in the following equation? 2O3 goes to 3O2. Okay, so let's just talk about this theoretically quickly, and then we'll move on. I don't know that we have time to actually go over an example like this right now, but I'm pretty sure there's one in the book. This might be the one in the book. So I'm going to be kind of light on examples today just because we have so much ground to cover right now. So how would these two compare? Let's say that the concentration of, or the rate of O3 is just X. Okay, if the rate of O3 is X, then what could I say about the rate? And actually, I should probably say negative X here, right? Because this is, the O3 is disappearing. So if the rate of O3 is negative X, then what could I say about the rate of the O2? The rate of the O2 should be 3/2 X. Okay, so I changed a couple of things. I made it positive, right, because the O2 is appearing, and then we took the stoichiometry into account here. All right. So you just have to be kind of careful with that. Know that the rate of the disappearance of one thing may not necessarily equal the rate of the appearance of something else if the stoichiometry is not the same. Okay? All right. Here's where, this I don't think is going to give you a lot of trouble. I actually kind of like this. It's kind of like a fun, I don't know. I mean, it's not that difficult of a puzzle, but it's kind of like a puzzle. What I'm going to tell you now may seem to contradict what I just told you, but to find the rate of a reaction, you actually have to perform experiments. You can't just look at stoichiometry to figure out rates. Okay, if we don't know any of the rates, now the stoichiometry is useful if we already know one of the rates, right? But if we know none of the rates, then really the only way to figure out the rate of a reaction is to do an experiment, okay? And when you do that experiment, you have to look at each individual reactant, and you have to see how it affects the overall rate of the reaction, okay? So what we have to do here, so we've got NH4 plus and NO2 minus are our two reactants here, okay? Now notice what we're doing. Can you tell what the strategy kind of is here with this experimental setup? What are we doing in this experiment? So from experiment 1 to experiment 2, for example, I'm doubling the concentration of NH4 plus, right? What am I doing to the concentration of the NO2 minus? Keeping it the same, okay? Now the reason we're doing that is because we want to see, all right, if I double the concentration of NH4 plus, what does that do to the rate of the reaction, okay? Turns out, if I double the NH4 plus concentration, it looks like the rate doubles. Can you see that? It goes from 5.4 to 10.8, okay? Now, is there another experiment on here that I could look at to figure out what happens with my NO2 minus? Yeah, what about 5 and 6, right? This goes from 0.202 to 0.0202 to 0.0404, but the NH4 plus is held constant in that case. Now, what happens to the concentration, or sorry, the rate, when I double the concentration of the NO2
Mr. Bowling,
minus?
contact the main office, please. Mr.
It
Bowling.
doubles again, okay? All right, so that's going to give us some useful information, okay? As the NH4 plus doubles, the rate doubles, and as NO2 minus doubles with the NH4 plus constant, the rate doubles, okay? So the rate is basically proportional then to NH4 plus times NO2 minus. So then we can write a rate law, okay? And basically that rate law is just, it's always written this way. They're always going to look like this. The rate is always going to come first. Then you're going to have this K, which is the rate constant, okay? Because this is proportional to. It's not equal to, it's proportional to. So we have to put a constant there. And then you've got your NH4 plus times NO2 minus. Now, if we had a situation where, let's say, the NH4 plus doubles and then the rate quadruples, there would be an exponent 2 here, okay? So basically, the experimental data tells us what exponents to put in our rate law, okay? So the fact that there's just a 1 and a 1 here tells us there should be, you know, this is first order with respect to NH4 plus and NO2 minus. I'm going to skip this stuff because, again, we got to hurry here. So for a general reaction with this rate law, we're going to say that it's nth order in reactant 1 and nth order in reactant 2. Okay? What that means is, if we've got, going back to the example that we had here, because this is kind of an understood 1 and this is an understood 1, then we say it's first order with respect to NH4 plus, and the reaction is first order with respect to NO2 minus. Okay? And what that is telling us, it's just telling us if we double the concentration of NH4 plus, we double the rate of the reaction. Okay? If we double the concentration of NO2 minus, we double the rate of the reaction. So essentially, whatever we do to the concentration of that species, that's going to be what happens to the rate of the reaction as well. If we triple it, reaction rate triples. Okay? A reaction can be 0th order. Okay? What does that mean if it's 0 order? It means that you can change the concentration all day and it's not going to change the rate of that reaction, which sounds a little odd, but there are certain reactions where certain reactants don't affect the rate at all, okay? And so you can change the concentration all you want, but they don't affect the rate of the reaction. Now, if you want to know the overall order of the reaction, you just add up M and N, okay? So for our example over here that we just did, what's the overall order of the reaction? 2. 1 plus 1 is 2. Okay? See, I told you this is easy. Okay, so problem here. Let's say you've got this reaction, and this is your rate law right here. Okay? So this is telling you the rate law. It says each of the following boxes represents a reaction mixture. We want to rank these mixtures in order of increasing rate of reaction. Oh, gosh. Okay, I'm sorry. We're going to go on. I'm almost positive this one's in the book, so the solution's there. You can look at it. I just need to make sure we get through all the rest of this. Overall reaction orders. Okay, you guys can do that too, right? Can we do that? If we've got the rate law. Now, again, don't look at the stoichiometry for reaction orders. You need to look at the rate law. Okay, so what's the overall order for this first reaction? 1, right? This is an understood exponent 1 right here on the N2O5, okay? What about the second one? 1.5. Can you do that? Yeah, you can have half orders of reactions, okay? We're not going to talk about that very often, but it does occur, okay? We'll usually stick to the whole numbers with our problems that we give you. The usual units of the rate constant for the rate law of the first equation. Okay, so let's think about this for a second. What units did we say we typically measure rate in? Molarity over seconds, right? So molarity per second is equal to K. Okay, that's what we're trying to figure out here. And then what do we usually measure concentration in? Molarity, right? So times M. So then if I solve for the rate constant, if I just solve for K here, then I'm dividing by M. So my K ends up equaling 1 over seconds. I guess I can just write 1 over S. Or seconds to the negative 1. Yeah, sorry, I'll just write S. Okay? S. Oh, S to the negative 1. I don't know.
What? Oh.
Oh, yeah, that's right. Yeah. Yep. That's right.
Wait, what?
Yeah. Yeah. Don't think about that. Okay. So this is your typical unit for the rate constant. Okay, in a first order reaction. Now, the second one would be different, but we're not going to worry about that for right now because again we are running out of time. But you see how you calculate for the units for the rate constant? Does that make sense? Okay. Using the initial rates to determine the rate law, you're going to be given problems like this often. Okay, this is the kind of problem that you'd have to solve. All right, so you've got your experiment here. Notice in the first experiment we're doubling B, did nothing to A. Okay, so what is the well, let's try this one because this one is going to be kind of like the ones that you'll actually have to do on a regular basis. So if I'm writing a rate law, rate is equal to K. You always put the K in there. Okay, and then my first reactant is A. What power is A going to be to here? Okay, this is a little tricky, right? So we need to look at experiment 2 and 3. You guys see that? Because that's where A is being doubled. Now, oh, okay, I'm sorry. 1 and 3 is what I meant. Because 2 and 3 is confusing because B is being halved there. So we don't want to do that, okay? But the two where B stays consistent are 1 and 3, okay? So in that case, we double A, and it goes from 4 times 10 to the 5th to 16 times 10 to the 5th. What happened when we doubled A? The rate quadrupled, right? So we need an exponent 2 there. This is a second order with respect to A because if I plug a 2 in here, 2 squared is going to give me 4, right? So let's say that we had an initial concentration of A of 1, and then we double that to 2. 2 squared is going to give me 4. So it'll increase the rate by a factor of 4, okay? So then with respect to B, what's our, what do we put for our rate law there? Yeah, this is a little tricky, but you double the concentration of B, nothing happens to the rate, right? It stays exactly the same. So this would be B to the 0, but you don't need to put that, okay? Usually when we have a 0 order, we just leave it out of the rate law. So there's your rate law right there. The rate equals K times the concentration of A squared, okay? And then it says find the magnitude of the rate constant. Now, how would we do that? Well, yeah, we have some data here, don't we? So just pick an equation or pick a reaction. It doesn't really matter which experiment you use. But our rate, let's say we use the first one here, plug that in for our rate, right? And then plug in our concentration for A, and then we can solve for K. So we could solve for the rate constant. Then you can also, does it ask for the units for the rate constant? No, it doesn't. That's surprising. A lot of times they'll ask for the units for K. In this particular case, what would the units for K be? Remember, rate is molarity per second, right? Is equal to K times, what would the units be for the A here? It's going to be a little different. M squared, right? Okay, so now you have to divide both sides by M squared. So then what you end up with is K is equal to 1 over seconds times molarity, or maybe slightly less awkward, seconds to the negative 1, molarity to the negative 1, whatever you prefer. Okay, I think I probably like this way of doing it a little bit better because I can keep track of my, I don't get fractions under fractions, and you can end up with that situation happening sometimes if you're not careful with this, okay? So that's the basic idea here. Is there anything else we need to talk about quickly? Because I know we're pretty much out of time. No, I think that's just, okay, good. Whew, we made it. That was a lot of stuff, though. So I would go back over sections 2 and 3 in the book, make sure that you get what this is talking about, okay? And we'll work on some practice problems when we get back to class, whenever that may be. All right, see you guys maybe on Monday.